to have. Okay. Hi, my name is Jack Baxter,
Hi, my name is Robair Farag.
and today we will be presenting our final project, Convolutional Neural Networks and Random Forest Classifiers for Enhanced Breast Cancer Diagnosis.
So for the agendas of today, we're gonna first start with the introduction, and then we're gonna go over the problem statement and goals that we have did for the project, and then we're gonna talk about the data and methodology, and then the model implementation. Then we're gonna go over the results and analysis, and then we're gonna provide with some discussions and insights that we had throughout the whole project. And then at the end, we're gonna end it up with some conclusion and future work. So for the first one is the introduction. After doing some research, 20% of mammograms are incorrectly dismissed as non-cancerous. Under 2024, recent advancements in convolutional neural network CNN algorithms have large implication in medical diagnosis tactics. How can we leverage AI to provide enhanced patient care and reduce disparities in oncology diagnosis? And on the right side, we got an image for a cancer, and then the image that is below, it's given an example of the input layer, and then the hidden layers, and then the output layers.
To guide our project, we drafted a statement to clearly outline the overarching problem with our data and how we aim to contribute to a potential solution. Traditional interpretation of mammogram data relies heavily on radiologists' expertise, image quality, and adequate accessibility to medical resources. Our project aims to harness the feature extraction and predictive capabilities of CNNs and random forests in a hybrid approach to mammogram diagnosis in order to provide a more advanced, equitable care to all patients. And below, we have a very simplified example of the workflow for our project. So starting first with raw mammogram data, moving into a CNN for feature extraction, and once you get that feature into a random forest prediction classifier, and then proper diagnosis or treatment once we have that prediction. In addition to our problem statement, Rob and I identified three specific goals we had for our project. First is to directly engage with our course content and apply the different programming and conceptual concepts we have reviewed this semester. Specifically, we chose to focus on convolutional neural networks and random forest classification, two different algorithms that we reviewed extensively in our lecture and our text. Second, through our project, we aim to engage with real-world problems in order to propose tangible solutions. In the medical field, oncology remains one of the most ambiguous divisions of healthcare research, and in our opinion, that assigns a degree of importance to any work done on the topic regarding AI or regarding oncology and healthcare in general. Lastly, by furthering development of hybrid AI models for oncology, we are actively contributing to the overall presence of AI for healthcare data. Hopefully, this will increase the awareness and familiarity of the technology and encourage use by more providers who might be lacking any reputable source or any reputable research with the algorithms themselves.
And next, we're gonna talk about some of the places that we found the data in it. The first one is a curated breast imaging subset of digital database for screening mammography. 2,620 scan full mammography studies, Belgian and Belgians. DICOM format, which stands for Digital Imaging and Communication in Medicine. We determined training and test sets, and then the last step was metadata CSV containing file path, tumor classification, and anonymized patient identification. And then at the bottom on the left side, if you look, we're gonna have a 2D and a 3D of a breast image that was done as a mammogram. And then on the right side, it's more in depth of what is the actual tumor looking at inside of it, or what is the actual scan that we found.
The CBIS DDSM dataset is public and very accessible for all types of research, which is greatly appreciated by anyone who's looking to employ the data in an AI algorithm. But to successfully download and use the CBIS DDSM set, the entire dataset needs to be downloaded to an external drive. With upwards of 2,000 mammograms and metadata for each image themselves, the 153.51 gigabyte set requires a special software to download the images and store them properly. For our project, we use the NBIA data retriever app, which produces a manifest file we could then utilize to directly access and download each image from the web. The workflow outlined below shows what we went through in order to get each mammogram, and it was great exposure and practice to deal with larger sets like this, especially how to properly access them from online sources, as that's an integral part in becoming more familiar and developing skills using big data, especially with AI algorithms. As mentioned previously, our main focus for our project was to create a convolutional neural network to perform image classification on the mammogram data that we downloaded. Specifically, we wanted to focus on a mass segmentation-based approach, as this is a strength for many CNNs that are used for image classification. More importantly, boundaries and edges on tumors can be identified easily on many different layers, even those within the network that have higher levels of abstraction, which was another pro to approaching our project topic with a CNN. Similarly, this gives us the ability to choose different feature extractions within the network for further analysis on the image, especially considering we wanted to integrate another AI algorithm. And in preparation for our project, we identified two of the biggest concerns that the larger AI community has with CNN usage in image classification, those being vanish or exploding gradients and the overpresence of false positives in classification. So, with those concerns in mind, we chose to utilize ResNet 50 as our chosen CNN model. ResNet 50 is a 50-layer convolutional neural network that is championed for its image classification and mass segmentation capabilities. More importantly, ResNet 50 addresses the vanishing gradient concern that we outlined previously, which a vanishing gradient occurs when weights utilized in the data processing layers of the neural network vanish due to backpropagation as the network goes back to earlier layers and relearns the image material. ResNet 50 includes a residual connections within the network, which facilitates more seamless data flow to previous layers in the network and reduces the need for backpropagation, leading to no vanishing gradient and more integrity in the neural network. Similarly, the hierarchical model of ResNet 50 promotes feature extraction, which was of specific interest to us, allowing us to further identify different patterns in data at different layers of the network and not just keeping it all kind of in a black box away from different ways we can interpret how the network is processing the image. And with that, we chose ResNet 50 because it checked a lot of those boxes.
And then the other methodology that we use in the algorithm selection was the random forest classifier, which it was easier because it was interpretable, reduces overfitting and noise. And then we had the ability to generate greater insights from CNN feature extraction. And then the last one is the identification of relevant features. And then below we can take a look at that image, which had the data set. We had the decision tree one and then the result, and then decision tree two, and then the result of it. And then the last decision tree dash n, and then the result of it, which made us using the random forest classifier. It was much easier for us because it helped us to reduce overfitting and noise and making great insights about some of the CNN extractions.
With all of our methodology in consideration, we wanted to provide an overview of our method. Once again, we aim to create a hybrid model to predict tumor classification with ResNet 50 and a random forest algorithm. Specifically, ResNet 50 will perform feature extraction at the penultimate layer, which is a layer of high abstraction from the original image. With that layer, we will take away those features that I identified, and we chose this layer as the optimal abstraction for defining boundaries of the image, which is an important part of math segmentation analysis. Both of the algorithms will compute their own overall prediction for each mammogram, classifying as either benign or malignant, and we will then compare the summary statistics and accuracy scores of each to provide a little bit of comparison and relativity for both of the algorithms that we've employed.
And for the model implementation, which code environment we use Visual Studio Code, and of course we use Python. And then we use Pandas, NumPy, and TensorFlow, and Polycom and sklearn. That's one of the AI solutions that we use. And then of course we use ResNet 50, and then the random forest, one of our methodologies for the AI. And then for the model implementation and data loading and processing, we use Pandas data frame for all metadata sets. And then we use the file path to DICOM mammograms in metaset. And then we converted the Benigen and Maligen label to binary 0-1 for efficiency. As we can see, we have provided some snippets of the codes in the actual presentation here to show what we did for the for the data frames and the metadata and the Benigen and Maligen.
In addition to the data pre-processing portion of this project, ResNet 50 has strict input requirements that all of the DICOM images were not going to meet. So in preparation of using ResNet 50, we had to resize and reformat each mammogram. And that included each image being 224 by 224 pixels with 3 dimensions. If it is a grayscale image, that last dimension is a single channel. If it is a colored image, which ours were not, the last dimension is 3 color channels. The image must also be formatted as an individual pixel array for machine learning, which is consistent with all of the other image classification algorithms that we've studied and practiced in our course thus far. And in order to properly format the DICOM image, we used a pre-written function that takes in the image as an argument and a target size, which has been adjusted for the ResNet 50 algorithm. It will adjust the size and then format and return the image for further processing as a pixel array, getting it all ready to go and formatted correctly for the ResNet 50 algorithm.
And next is the model implementation for loading the base model. We pre-trained the initialization of base ResNet 50 from Geeks for Geeks. We use the Imagine because it has large generalized training with capabilities to fine-tune if needed. Its specified input shape to match pre-processing limited label data in mammogram set because it was unable to train ResNet 50 from scratch, so we had to use it in order for us to train it from the beginning. As we can see on the right side, that code ResNet 50 weights equal imagine it include. If it's false, we gotta change the shape of it.
So once the base model of ResNet 50 has been trained with ImageNet, we wanted to add additional layers that are trained or fit on the image data specific to our mammograms, and we are able to add them onto the model that has already been trained by ImageNet. While the bulk of the model is pre-trained, this allows for customization of ResNet 50 to our set, and there are a variety of adjustable hyperparameters to further train deeper the already pre-trained ResNet 50. That includes more foundational layers for more in-depth analysis down the road. Our ResNet 50 model was properly fit and trained with the images provided by CBIS DDSM. Predictions were made based on the trained data with our test set, and accuracy statistics were garnered from those predictions to efficiently take a look at how well our ResNet 50 model was performing.
And for the model implementation for the random forest, We use the extraction of embeddings from intermediate to penultimate layer, consisting of training and test sets from the original metadata to help us to see what is going to happen in the future steps that we're going to take. Initialize a random forest classifier. We use n estimators equal 100 and random state equal 42, consistent with widespread use of RF. And then to fit the RF classifier to the training embedders vector of image, we perform a predictions for tumor diagnosis, and below you can see some of the examples and snippets of the training that we did for the tumor predictions. And what results and analysis that we got by using ResNet 50, it's provided us with some accuracy and loss curves by epoch. On the left side, we can see that an image of an accuracy of 0.50 for the epochs, and then the validation accuracy you can see on the left side also is as 0.60, and then going down to 5, and then coming up back up to 6, and then going into a straight line. And then on the right side we got the model loss over epochs. The blue line represents the training loss, and then the orange one, which is the validation loss. You can see that the training losses were up high, and then it got very quickly to go as low as much as it could.
At the end of our ResNet 50 model run through, we had an overall accuracy and prediction of 61.11%, with large implications in different ways that we could improve the model. It was still an accomplishment to get the model up and running, especially considering the formatting complications with the DICOM images. And like I mentioned, there are many implications as to how we can improve this accuracy score.
And the results and analysis of the RF, you can see on the right, we got overall accuracy of 48.41% for the data set, and on the left side, you can see the Benjamin and Melge test scores that we got, which is kind of pretty high because it's always an issue to have an overall accuracy for predicting if that person or that patient is going to have cancer or no. It's kind of hard because each case is different than the other one. So we got an overall accuracy of 48.41%. And then the result and analysis of the comparing algorithm, you can see the difference between the resonant and the random forest, which one got a more accuracy, which is resonant got 60% accuracy, and the random forest around like 48%. So that's why we decided with resonant is much better for accuracy. That's how it's gonna help us in the future to train it more and have more accuracy for the algorithm that we're gonna use to train the data sets.
As we reflect on the different accuracy scores from our two algorithms with our data, it's important to keep in consideration that this is binary data we are predicting. So it is either a benign or a malignant tumor. In the code, it was 0 for benign, 1 for malignant. In further investigation of the accuracy score and how significant that score might be, we performed a very quick histogram just to check for any class imbalance. And we found that the distribution of pathology labels was roughly 50-50, 50% being benign tumors, 50% being malignant in the test set, meaning that our accuracy scores sitting around 50%, give or take, means that it is expected for an algorithm to be, if it were to randomly guess on the set, we would still get an accuracy of around 50%, um, which is even more of an indication that there are different ways we can improve our model. And taking, those scores into consideration and just trying to find more insight as to how significant they might be was also a huge portion of this project. That being said, there are a variety of different modifications we can make to our algorithm down the road. First being to open or unfreeze the deep layers of ResNet 50 for training the image data. As we explained earlier, we went ahead and utilized ImageNet for all of the training to make sure that our ResNet 50 was being trained comprehensively and not overfit to the tumor set that we were dealing with. In future directions or future ways we can expand on this project, we could open or unfreeze those deeper layers and have them trained on the image data as well. And that would look like us just adjusting the base model trainable parameter to true. Right now it's set to false. Second, it would probably be worthy of time to take a look into the investigation of the pixel normalization tactics we used. As we outlined earlier, there were pretty significant data pre-processing um, conversions between the DICOM data and what was suitable for ResNet 50. It would be important to take a look there and make sure that it didn't skew the validity or mess up any quality of the DICOM image itself before it went into the algorithm. Lastly, the inclusion of hyperparameter tuning is an important consideration to have. We did not make any modifications to our hyperparameters, even in light of different baseline learning rates or batch sizes to meet what might be optimal for our ResNet 50 model and the data that we're doing or using. So that is another way that we might be able to improve our model down the road and improve the accuracy score.
And finally, some of the conclusions that we came to it. So traditional interpretation of mammogram data relies heavily on radiologist expertise, image quality, and accessibility to medical resources. Our project aim was to harness the feature extraction and predictive capabilities of CNNs and random forest in a hybrid approach to mammogram diagnosis to provide more advanced, equitable diagnosis to all patients and to help them in the future to make it more easier to see if they're gonna get cancer or no. And as we can see down below from the images from the raw mammogram data to the CNN feature extraction, and then to the random forest prediction, and then the proper diagnosis and treatment. And then we created hybrid CNN and RF prediction models. We practiced deep learning images and classification and strategies. We focused on interpretable advanced application of AI for oncology. We tried to conversion of DICOM to analyzable format, extraction of important feature data, and then employ transfer learning techniques to best prepare the model for the future, compared and evaluated various AI approaches to real-world applications as much as we can.
In addition to the future directions outlined a few slides prior, the dataset CBISDD-SM also includes different ROI masks or region of interest masks and cropped images that will guide algorithms to really specific regions on the tumor that might lead to greater insights or greater importance, especially in weight as you're navigating the neural network. So inclusion of those files might be a way to improve the algorithm moving forward. Similarly, to investigate the accuracy score at each layer of the ResNet 50 would best identify where in the image analysis process the algorithm was having trouble. And once you can identify that, there are different ways you can tune the hyperparameters or focus on feeding more high quality data into those layers to improve the overall accuracy. That is all we have regarding our final project. Thank you for taking the time to listen to our presentation today and have a great holiday break. Here are the sources.